Good morning. Now, today, once again, we will see some applications of machine vision system or robotic vision system. Therefore, introduction to machine vision system. A machine vision system is a type of technology that enables a computing device to inspect, evaluate, and identify still or moving images. It is a field in computer vision and is quite similar to surveillance cameras, but provides automatic image capturing, evaluation, and processing capabilities. Machine vision is the automatic extraction of information from digital images. A typical environment would be a manufacturing production line where hundreds of products are flowing down the line in front of a smart camera. Manufacturers use vision systems instead of human inspectors because it's faster, more consistent, and doesn't get tired. The camera captures the digital image and analyzes it against a predefined set of criteria. If the criteria are met, the object can proceed. If not, the object will be rerouted off the production line for further inspection. Major applications of machine vision system. Measurement. A common machine vision application is automated measurement. After an image of a part is captured, the software compares the measurement to a required tolerance. For example, in factory automation, machine vision systems are used to measure the gap in a spark plug, ensuring it meets the tolerance required to function properly. In the packaging and labeling industry, machine vision is used to measure the fill level of a water bottle, ensuring it was filled to the correct height. Next is counting. Another common machine vision application is counting, looking for a specific number of parts or features on a part to verify that it was manufactured correctly. In the electronics manufacturing industry, for example, machine vision is used to count various features of printed circuit boards to ensure that no component or step was missed in production. Location. Machine vision can be used to locate the position and orientation of a part and to verify proper assembly within specific tolerances. Location can identify a part for inspection with other machine vision tools, and it can also be trained to search for a unique pattern to identify a specific part. In the life sciences and medical industries, machine vision can locate test tube caps for further evaluation, such as cap presence, cap color, and measurement to ensure correct cap position. Decoding. Machine vision can be used to decode linear, stacked, and 2D symbologies. It can also be used for optical character recognition, which is simultaneously human and machine readable. In factory automation, machine vision is used to sort products on a production line by decoding the symbol on the product. The symbols themselves can also be verified by machine vision based verification systems to ensure that they comply with the requirements of various symbology standards organizations. Therefore, what are the benefits of machine vision system? First is reduce defect, ensure fewer bad parts enter the market which cause costly recalls and tarnish a company's reputation. Prevent mislabeled products whose label doesn't match the content. These defects create unhappy customers, have a negative impact on your brand reputation, and pose a serious safety risk, especially with pharmaceutical products and food items for customers with allergies. Then second is increased yield. turn additional available material into sellable products, avoid scrapping expensive materials and rebuilding parts, reduce downtime by detecting product routing errors that can cause system disruptions. Then tracking parts and products, uniquely identify products so they can be tracked and traced throughout the manufacturing process. Identify all pieces in the process, reducing stock and ensuring product will be more readily available for just-in-time processes. Avoid component shortages, reduce inventory, shorten delivery time. Then comply with regulations. To compete in some markets, manufacturers must comply with various regulations. In pharmaceuticals, a highly regulated industry, machine vision is used to ensure product integrity and safety. By complying with government regulations such as 21 CFR, Part 11 and GS1 data standards. Now we will see components of machine vision system. First is lighting. This critical aspect of a machine vision system illuminates the part to be inspected, allowing its features to stand out so that the system can see them as clearly as possible. Lens captures the image and presents it to the sensor in the form of light. Sensor converts light into a digital image for the processor to analyze. Vision processing consists of algorithms that review the image and extract the required information. Communication, the resulting data is communicated out to the world in a useful manner. Therefore, we will see this video. Please use earphone to listen this video. Please wait for 2 minutes. I will bring sound box. Within 2 minutes, I will come. Okay, 1 minute.
Welcome to Microscan's
Okay, now
Introduction
listen.
to Machine Vision, an educational webinar series to help new users better understand the basics of machine vision technology. This is the third presentation in our series, and in this installment, we'll talk about the key parts of a vision system. If you've tuned into our previous presentations, then you're already familiar with some of the applications of machine vision and the benefits it brings to the production process. There are typically 5 components that make up a machine vision system. They include the lighting, lens, sensor, vision processing, and communication. Here you can see 2 examples of different types of machine vision systems. On the left is a system made up of assembled components, which includes a PC and a camera, along with external lighting to illuminate the part. On the right is an integrated system, or smart camera, where all of these components are built into a single device. Choosing the right configuration depends on the requirements of your application. Lighting is a critical piece because it illuminates the part to be inspected, allowing its features to stand out so that the camera can clearly see them. Next, you have the lens, which captures the image and presents it to the sensor in the form of light. The sensor in a machine vision camera converts this light into a digital image, which is then sent to the processor for analysis. Vision processing consists of algorithms that review the image and extract required information. Then the system will run whatever measurements or other processes it has been instructed to run. Finally, the resulting data is communicated out to the world in a useful manner. Before we take a closer look at each one of these components, it's important to note that the part itself is a consideration. How will the part be presented to the vision system? Part placement and orientation should be consistent and repeatable to achieve the best possible results. Proper lighting is critical to the success of an application. The type and position of a light should be carefully selected to maximize contrast of the features you plan to inspect and minimize contrast of everything else. This is like an electrical engineer setting up a system to give a high signal-to-noise ratio. You're trying to make the pieces you need to see or need to measure very clear, and you want all the other items in the image as invisible as possible. To give you an idea of how you might do this, let's look at some examples. Here are two photos of the same light bulb, and let's say that the objective is to see the tungsten filament between the two conductors. In the image on the left, the light is between the camera and the part. On the right, the light is behind the part, away from the camera. In the front lit image on the left, it's quite hard to see where the filament is. But in the backlit image, you can clearly see the filaments, making it very easy to check its presence and position. In this case, the light's position is critical. Here's another instance where the position of the light impacts the image significantly. In these images, the same part is lit with the same light. On the left, the light is placed near the camera lens. In the image on the right, the light is positioned lower and closer to the part. This clearly makes a big difference in the way the data matrix code shows up, as well as the outline of the part. This pair of images shows foil packaging with a printed expiration date. The light is positioned between the camera and the part in both instances, but a different type of light is used in each case. The example on the left is lit with a ring light, and clearly you would have a tough time locating, let alone reading the text in the image. The right-hand image, however, shows the same part lit with a dome light. You can see how dramatically the lighting changes the appearance of this part. In this case, it's the type of light that affects the image. If you can't see the necessary feature on a part, you can't measure it or read it. Proper lighting is key to acquiring a quality image with clearly visible features. Next, we'll discuss the lens. The purpose of the lens is to capture the image and deliver it to the sensor. The lens will determine your field of view, depth of focus, and your focal point. Generally, you'll find one of two different lens types in a vision system: an interchangeable lens or a fixed lens. Interchangeable lenses are typically C-mounts or CS mounts. The right combination of lens and extension tube will acquire the best possible image. A fixed lens is part of a fully integrated smart camera. Fixed lenses typically use autofocus. This could be a mechanically adjusting lens or even a liquid lens, and it will automatically focus on the part. Autofocus lenses usually have a fixed field of view at a given distance. Lens choice can dramatically affect the appearance of an image. Here are two examples that were taken with the same camera using different lenses. The image on the left was taken using a 12mm wide-angle lens. This lens provides a larger field of view and less magnification than the image you see on the right, which was taken using a 25mm lens. If you use a lens with a longer focal length, you will magnify the image and reduce the field of view. The lens delivers the image to the sensor in the form of light. The sensor typically uses CCD or CMOS technology to capture this light and convert it to a digital image. When you zoom in on this digital image, you can see that it's a collection of pixels. Low light produces dark pixels, while bright light creates brighter pixels. It's important to ensure your camera has the right sensor resolution for your application. Here's an example of the same image captured at different resolutions. On the left is an image captured with a 0.3 megapixel sensor. also known as a VGA sensor. On the right, the same image is captured by a 2-megapixel sensor. You can see that the image on the left has much less resolution and is more pixelated. The higher the resolution, the more detail an image will have, and therefore, the more accurate your measurements will be. The size of your parts, tolerances, and other application parameters will dictate your required resolution. The next step is vision processing. The processing function is truly at the core of machine vision, the mechanism for extracting the information that is required of an application. Processing the image may take place externally in a PC-based system or on board in a smart camera. Vision processing is performed by software with a wide variety of interfaces and tools available. Some common vision software tools include locate, count, measure, and decode. Tools are often used in sequence to achieve a desired result. A typical example of this is an inspection application that uses a locate tool to locate a cap on a bottle. The measure tool then measures its height to ensure that it's properly seated on the bottle. Vision processing consists of several steps or algorithms performed by the software. First, the image is acquired from the sensor. In some cases, pre-processing may take place to optimize the image and ensure that all the necessary features stand out. The software then finds the features that it's supposed to look for, runs measurements, and compares these to the specification. Finally, the results of these measurements will be communicated as pass or fail. This brings us to our fifth component, communication. As discussed earlier, the purpose of machine vision is to extract useful information from digital images. The communication of that data is critical. Typically, this is done by either a discrete I/O signal or data sent over a serial connection to a device that's logging information or using it. Many smart cameras have these connections built into them. Discrete I/O points may be connected to either a PLC, which will use that information to control a work cell or an indicator such as a stack light, or directly to a solenoid, which might be used to trigger a reject mechanism. Data communication by a serial connection can be in the form of a conventional RS-232 serial output, or Ethernet. Some systems employ a higher-level industrial protocol like Ethernet IP, which might be connected to a device like an HMI screen, as shown here, to provide visual confirmation that the system is running. Let's look at how these different parts work together to create a machine vision system. In this example, we are inspecting the fill level and cap alignment of water bottles. We'll begin the process by triggering the inspection when the bottle comes by. This will trigger the lighting to illuminate the bottle so that the camera can clearly see the necessary features. The lens and sensor will then capture and create a digital image and deliver it to the processor, which in this case is a PC. The software platform running on that PC will extract the required measurements to ensure that the fill level is correct and that the cap is properly seated on the bottle. The current status of this process can be communicated to and viewed on an HMI screen. Other actions may also take place based on the results of the inspection. So let's review. Machine vision systems may be integrated, such as a smart camera, or they may contain multiple components, such as a gigabit Ethernet camera solution. The 5 key components are the lighting, lens, sensor, vision processing, and communication. Lighting is critical to the success of a machine vision application and should make the features you're going to inspect stand out. The lens captures the image and delivers it to the sensor in the form of light. The sensor converts the light into a digital image. The processor uses software algorithms to extract useful data from the image and determine the results of the inspection. These results are then communicated in a useful manner. If you missed the previous presentations in this series, you can find them on our website at www.microscan.com, as well as additional machine vision resources, including white papers, case studies, and videos. Thanks for watching.
Okay, thank you. Now we will see another video, that applications of a machine vision system. Please wait for 1 minute.
Welcome to Microscan's Introduction to Machine Vision, an educational webinar series to help new users better understand the basics of machine vision technology. This is the first installment in our series, and over the next 10 minutes or so, I'm going to talk about what machine vision is and how it's used in factory automation, along with the 4 most common applications of the technology. So let's get started with a definition of machine vision. Machine vision is defined as the automatic extraction of information from digital images. So what exactly does that mean? Well, let's look at a very basic breakdown of a typical machine vision process. First, you have a manufacturing production line with a steady flow of objects. Then you have a camera or optical system trained on the line. Next, you make sure that you have proper lighting of the line so the camera can see the necessary details. The camera captures digital photographs and analyzes the images against a defined set of criteria. That's in an industrial context. There are different types of vision that are used for other purposes, but when we refer to machine vision, we're talking specifically about industrial vision as it's used in a manufacturing environment. Manufacturers use automated machine vision instead of human inspectors because it's faster, more consistent, and works for longer periods of time. Vision technology got its start in the 1950s, but the widespread use of machine vision in industry arose in the 1980s and 90s. This photo, taken from the Wikipedia entry on machine vision, shows a pioneering demonstration at a 1983 trade show of a system by Automatics, which is now part of Microscan. Of course, machine vision has come a long way since then and is now used for many different valuable processes in manufacturing. Let's talk about some of the most common applications of machine vision. As it has developed, machine vision's applications have grown into 4 basic functions: measurement, counting, location, and decoding. Since its start, machine vision has been widely used for measurement. And by this, we mean the automated measurement by a machine. That measurement can then be checked to a specified tolerance. For example, something we've been doing for years with machine vision is measuring the gap in spark plugs. As you may know, this gap needs to be a certain width, or the car won't run as well. Therefore, this gap measurement is an extremely critical spec for the part. We can use a camera and measure the spark plug gap by machine. This eliminates the need for a person to be there to measure and adjust the gap manually. We can automate the process and do it more quickly and accurately. Counting is another typical machine vision application. There are a few different tasks that fall under this category, but basically, counting means to look for a number of parts or a number of features on a part. This allows us to locate missing parts and ensure that products are assembled properly. This example shows an aluminum flange with some holes drilled in it. If you count the number of holes, you'll see that there are exactly 8 of them. Assuming that we wanted 8 holes, we know that the drilling process was done properly. Another counting function is absence, presence. Is it there or not? Here we have an 8-pack of sodas, and you can see that one of the sodas is missing. With machine vision, that packaging can be checked to make sure an incomplete pack doesn't make it to the grocery store shelf. We've slowed the process down so you can see it, but machine vision systems can operate much faster. Location is when machine vision is used to report the position and orientation of a part. This may be done for several reasons. We can locate the position and orientation and then check that to a specified tolerance. So, in other words, you're looking at the part to make sure that it's at the correct angle and using that as a reference point to verify proper assembly. You can also use this for alignment to other machine vision tools. Let's take our spark plug example. This is a very powerful feature in machine vision. Your parts may be facing all different directions as they go down your production line, and you can locate a part, straighten the image, and then you can run other machine vision processing tools on it. Additionally, you can find a unique pattern and use that to identify a part. An example you can see here is a can of soup. The vision system has been trained to look for a pattern on the soup. In this case, the portion of the label that says tomato on it. We can use that pattern to verify that we do, in fact, have the right soup going down the line. Decoding refers to the decoding of 1D and 2D symbologies, such as linear barcodes, stacked symbologies, as you see here, and 2D symbologies, such as data matrix codes. This also refers to OCR, or optical character recognition, which is text that is simultaneously human and machine readable. Decoding is typically used to record information as historical data. That way you have a record of parts that have gone through a process. You can track the path that a part took through that process and use that data for immediate action, meaning that you can look at the data and sort based on what it says. You can also validate the data for correctness. When you read a marked code on an object, you can verify that the data in the mark is correct, or that the format of the data is correct, or that you have the correct product going down a production line. An obvious question here is, why use machine vision to do this when dedicated auto ID systems would do the same thing? You might think of machine vision as auto ID or barcode reading plus. The plus is the ability to run other measurements and operations in combination with the reading of barcodes or text. For example, you might want to read a label and also check that it's properly aligned to the product. In other cases, you may need the ability of a machine vision system to tackle tougher applications that require more capability in terms of image pre-processing, or in the case of a PC-based system, sheer speed and processing power. An example of this sort of application is reading the OCR code on a can of vegetables during a high-speed canning process. You may not realize that when vegetables are put into cans, they are usually done so with no labels, and the only indication of what's inside is a text code on the end of it. When the time comes to put the label on the can, a vision system checks the code on the end of the can to make sure that the right vegetable is inside the can and matches the label. So let's review. Machine vision is the automatic extraction of information from digital images. And we talked about the common manufacturing applications of machine vision, which generally fall under 4 basic functions. measurement, counting, location, and decoding. The visual examples we've shown you here are mostly slowed down so you can see what's happening. In reality, machine vision can operate much faster, processing hundreds, or in some cases, even thousands of pieces per minute. But that's just one of the many reasons manufacturers are using machine vision. Be sure to check out the next installment in our series, Why Use Machine Vision, where we'll take a look at the benefits of this technology. And for more machine vision resources, including white papers, applications videos, and online tutorials, be sure to visit our website at www.microscan.com. Thanks for watching.
Okay, now next, lighting techniques. Now already we have seen lighting technique is one of the important technique in the machine vision, because with the help of light only that object is focused, or we can take picture of that object. Therefore, there are different types of lighting techniques. First is backlighting. Backlighting generates instant contrast as it creates dark silhouettes against a bright background. The most common uses are for detecting the presence or absence of holes and gaps, part placing or orienting, or measuring objects. Often it is useful to use a monochromatic light such as red, green, or blue with light control polarization if precise edge detection becomes necessary. Next is diffuse lighting, hemispherical, that is full bright field. Diffuse or full bright field lighting is most commonly used on shiny, specular, or mixed reflectivity samples, where even but multidirectional light is needed. Several implementations of diffuse lighting are generally available, but there are three primary types, with hemispherical dome or cylindrical or on axis being the most common. Diffuse dome lights are effective in lighting curved specular surfaces commonly found in the automotive industry. The next is diffuse full bright field lighting, on axis diffuse. On axis light works in a similar fashion for flat samples and are particularly effective at enhancing differentially angled, textured, or topographic features on relatively flat objects. To be effective, diffuse lights, particularly dome varieties, require close proximity to the sample. Then diffuse full bright field lighting, flat diffuse. A useful property of axial diffuse lighting is that in this case, rather than rejecting or avoiding specular glare, you may actually take advantage of the glare if it can be isolated specifically to uniquely define the features of interest required for a consistent and robust inspection. See that this is the hemispherical lighting. Hemisphere is used to focus or to focus with the help of light on object. This is full bright field, and this is diffuse lighting, flat diffuse. These flat surfaces are used to for illumination. Then partial bright field or directional lighting. Partial bright field lighting is the most commonly used vision lighting technique and is the most familiar lighting used every day, including sunlight. This type of lighting is distinguished from full bright field in that it is directional, typically from a point source, and because of its directional nature, it is a good choice for generating contrast and enhancing topographic detail. It is much less effective, however, when used on axis with specular surfaces. generating the familiar hotspot reflection. Then dark field lighting. Dark field lighting is perhaps the least well understood of all the techniques, although you do use these techniques in everyday life. For example, the use of automobile headlights relies on light incident at low angles on the road surface, reflecting back from the small surface imperfections and also nearby objects. Dark field lighting can be subdivided into circular and linear or directional types, the former requiring a specific light head geometry design. This type of lighting is characterized by low or medium angle of light incidence, typically requiring close proximity, particularly for the circular light head varieties. Now we will see the videos.
Hello and welcome to this Gardasoft presentation on 6 key considerations for machine vision. Lighting and lighting control are sometimes thought critical only in complex machine vision configurations. In truth, they can be just as vital in the simplest of applications. Lighting and lighting control are vital elements of machine vision because they have a massive influence on the quality of the captured image. Machine vision software can only deliver intelligence from information present in the captured image. So optimizing the lighting should be an essential consideration for every application. This presentation reviews 6 key considerations for obtaining effective machine vision lighting. We'll look at the quality of the image, and then we'll go on to getting the most out of your LEDs, how important it is for flexibility, looking at the relevance for illumination stability, making easy setups, and utilizing your network capability. Optimizing your image. The best possible camera image has optimum levels of contrast and signal to noise ratio. These 2 measures are determined by the amount and quality of the light falling on the camera sensor. Reduced light levels increase image noise and reduce contrast, making it more complicated to process the image and consequently more difficult for the purposes of accurate measurement or product classification. In addition to ensuring that the right amount of light reaches the camera sensor, it's also essential to ensure that light levels are consistent. Variable light intensity can result in poor measurement repeatability, with major repercussions in a manufacturing environment, leading to excessive waste, defective product reaching the end user, or even line stoppages. Attempting to use image processing software to enhance low-quality images is often both time-consuming and ineffective. Crucially, image processing can only manipulate data that is captured by the sensor. It cannot create information that is not present in the original image. Therefore, it is the quality of illumination that defines the intelligence available, and both lighting and the way lighting is controlled in a machine vision system should be carefully considered. Providing inadequate lighting control is likely to lead to significant underperformance from the machine vision system. This slide shows a simple example of how reducing light intensity on a fast-moving object correlates directly with reduced image quality. Longer camera exposures are required to compensate for reduced lighting intensity, which in turn leads to motion blur. Getting the most from your lighting. As described earlier, delivering the correct amount of light into the scene is critical to getting accurate, reliable results.
LED lighting is generally specified as either 12 volt or 24 volt supply, but the brightness is determined by the amount of current running through the LEDs and not the voltage across them. This means that good current control is necessary to accurately adjust the light intensity. In addition, LEDs heat up during use, and this changes both their forward voltage and their efficiency, so that brightness will vary over time. LEDs are remarkably reliable devices, but their light output will deteriorate over time as a consequence of repeated heating and cooling cycles. Typically, an LED would be replaced when its output falls to below 70% of its initial rating. Driving an LED continuously will generate the most heat and create the lowest device lifetime. Switching the light on only when an image is being acquired by pulsing the light will minimize the amount of heat produced and significantly improve LED lifetime. Pulsing can be achieved most easily by using a lighting controller to manage the strobing. Converting a constant illumination system to a strobe system is straightforward when using a quality lighting controller. The trigger for the camera is set to the lighting controller, which allows adjustment of pulse length and intensity, and any delay between trigger and output pulse. This ensures that the lighting pulse occurs consistently at the same point in the camera exposure, and that the total light energy is identical for every image. A lighting controller also allows the total light output to be managed to balance the intensity needed against the need to maximize LED lifetime. Strobing an LED light brings significant benefits because when the timing and duty cycle are carefully controlled by the controller, the light can be overdriven to achieve light intensities much higher than the manufacturer's light rating. This is an extremely useful technique in many scenarios. For example, if the inspection speed increases and a shorter camera exposure is needed, overdrive can provide the additional intensity required necessary to maintain image quality. Pulsing the light also allows the image capture of objects moving at high speed without image blur, as I mentioned earlier. Gardasoft controllers have fine adjustment of pulse timing, which is often more accurate than the camera's internal timing. While overdriving is a very powerful technique, it is necessary to ensure the LED is not driven at too high a current for too long, which may damage the light. Gardasoft has developed SafeSense technology to impose safe working limits on overdrive based on manufacturer specifications, pulse width, and duty cycle. SafeSense technology also ensures that the maximum current rating for the LED is not exceeded during continuous operation. The heat generated within the controller itself must also be controlled, and Gardasoft designed its Safe Power technology to minimize the heat dissipation in the controller by automatically adjusting the lighting supply voltage. This allows lighting to be driven with high continuous currents without heat sinking the controller. I'm going to take you through 3 slides now showing an example of a benefit from overdriving the LED lighting. Here we have an object requiring 2 surfaces to be in focus. Under nominal conditions, only the top surface is in focus. The natural thing to do would be to stop down the aperture to increase the depth of field. To increase the depth of field by stopping down makes the image too dark. By overdriving the LEDs by 400% brings the image back to a satisfactory condition for processing. Building in flexibility. A common occurrence in machine vision systems is for the requirements or the working environment to change. One of the most compelling benefits of including a lighting controller in your lighting system is the flexibility the controller brings in adapting to changing requirements and environment. If the system is configured to use continuous lighting, the inclusion of variable lighting control allows the intensity to be adjusted to suit the application, meaning that the same lighting can be used with different intensity settings for different product batches. For example, the inspection of reflective objects would require a lower brightness than would be needed for objects with more diffuse surface finishes. The ability to switch to pulsed mode can also lead to a reduction in average power consumption and an extension of lighting lifetime. Making use of overdrive mode for LED lighting offers even more flexibility without requiring hardware change. Operating in continuous mode, the controller can be set up for any inspections requiring light intensity up to the 100% of the LED rating.
Okay, now we'll stop here. Thank you very much. Thank you. Thank you very much.